In this example right here, I have a tube here that has a closed end due to the water and an opened end here due to the air. I've got a tuning fork here that has a frequency of 384 Hertz. You might hear a really high-pitched squeal, but you're not hearing the actual G note right now. And if I put it over top of this tube, it's a little bit louder, but not really. The question is, how long does this tube need to be so it amplifies the sound? Go ahead and try that out, and then we'll take it up. And if I put it over top of this tube, it's a little bit louder, but not really. The question is, how long does this tube need to be so it amplifies the sound? Go ahead and try that out, and then we'll take it up.
So what do we want to know? Well, we want to figure out the wavelength that's being produced so we can figure out their harmonics. First thing we need to do is solve this equation here. So the speed of sound, or speed is equal to wavelength times frequency. So we know the speed of sound in this case is traveling through the air, so it's going to be 332 plus 0.6 times the temperature in degrees Celsius. Now we know the temperature in the room, we can measure that. We know the temperature in here is 22 degrees Celsius. And we also know the frequency of this tuning fork we're looking at is 384 Hertz. So let's go ahead and start plugging in. So 332 plus 0.6 times 22. And what we find is that we have a speed of sound of 345.2 meters per second. So now we've got enough to go ahead and plug into this equation here. Because we know it's going to be 345.2 is equal to wavelength times 384. So in this particular case, we know it's going to be 345.2 divided by 384, which is the wavelength, which is equal to 0.899 meters. So from here, what we can do is we can start to figure out the harmonics. Now, because this is an example of a fixed end and an open end, we know the formula is going to be for the first harmonic, length is equal to 1/4 of a wavelength. Let me make that neater. And length here for the second harmonic is going to be 3/4 of wavelength. So now let's go ahead and let's plug those in. So length is equal to 1/4 times 0.899, and that's going to be equal to 22.5 centimeters. Or actually, let's keep the units the same, 0.225 meters. And for our second harmonic, yet again we plug in, and that's equal to 0.674 meters.
So now that you've solved the question, you know the answer is going to be around 22.5 centimeters and 67.4 centimeters. Let's go ahead and try this out. So we're going to go ahead and shut this up. So this will be the first harmonic, and if we go ahead, we can't really hear the note, but if we put it over top, we can hear a big difference. Now that's because that is exactly 1/4 of the wavelength. If we were off, and I go ahead and try this experiment, you see it doesn't work nearly as well. So now if we go to the second harmonic, which is 3/4 of a wavelength, that's going to be at 67.4 centimeters. We'll go ahead and try this again. Yet again, because it has 3/4 of a wavelength right here, we can see how loud it gets.